Okay, so welcome everyone to lecture 3 of the computer vision course this fall quarter. So a few weekly logistics. I think this is something that you're familiar with. Is there anything that anyone wants to share on the logistics side that we haven't covered yet? Is there anything someone wants to ask? Or anything, any thoughts? Okay. All right. So hopefully you are going to the office hours, quiz sections, and using all the resources available for you. Um, so if anything else, just feel free to share. Yeah. Okay, here are the references for today's lecture. There's one on SVD, which I shared last time. There's one on convolutions. There's a nice webpage on Convolution Playground where you can go and play around with different convolutions. And there's also the, this is for future, right? So we don't need it right now, but for future reference. If I encounter some more good resources as we go, we'll definitely share it. Okay, just wanted to remind you on this as well. So hopefully you were able to, figure out the polls. Pretty soon we would be using the polls to, so as long as you're participating in the in-class exercise, we're not going to be checking on the answer specifically. But if you're, putting in your answer to the polls, that will count towards your in-class grade. So just make sure you're like participating in the polls. And if you're not, I posted a message on Discord. So if you're having difficulty accessing for some reason, because I know there's new folks who've never used the poll before are able to access it. So I'm assuming you should also be able to do that. But if you are having a difficulty, feel free to message me or the TA Ayush. Okay, cool. All right, so let's move on to today. So today we'll be continuing from the last lecture. We'll be looking at some SVD and image applications. And I know a lot of questions came up last time on the use cases for SVD and how do we understand matrices better and all of that. So some of this is just matrix algebra, right? If you're solid on matrix algebra, you will get it. But if you're not, it's a good opportunity to kind of refresh your concepts in matrix algebra and understand. So this is like, where math, machine learning, image processing, all of these things intersect. You have a real problem, you want to do something with an image, but hey, guess what? You need to represent it as a matrix. Well, if you're representing it as a matrix, you need to do something with it, and that's where matrix algebra comes in. And that interfaces again with coding, right? So you want to do some coding and manipulate matrices. You need to know what algebraic operations you're doing there. So that is understanding. That's also called modeling. Taking a business problem, or let's say you're working at industry, right? You're taking a business problem that you want to solve and modeling it as computer vision problem or a machine learning problem. That has a lot of weightage in the grand scheme of things. That's like, no one's going to tell you, hey, why don't you solve this clustering problem using k-means on this data set? No one's going to tell you that. They're going to be like, we want to improve our business by 10%. What can you do about it? And then you have to figure out, oh, I guess we can use some machine learning here or computer vision here. And then you work backwards from the goal, and then you decide how to model it. Maybe you need to do some image processing, or let's say you're taking NLP class, or you have NLP data, and you'll be doing natural language processing. So there is that component. And then once you do that, then whatever we cover here in this lecture will fit in and fill in the missing pieces, right? So that is something for you to ponder on. So we will have opportunities every lecture. We'll be looking at some of this modeling. So we call it machine learning modeling. So modeling refers to taking something in the business context and applying, appropriate machine learning approach to it. right? So we'll have opportunities to look at different ML modeling use cases in every lecture, right? We'll also do a matrix arithmetic refresher. How many of you feel this would be useful? Just a show of hands. Okay. All right, I see quite a few hands going up. All right, so we'll do some refresher on matrix arithmetic. So feel free to have your notebooks and pen, or if you're using an iPad, have your pencil ready so you can actually work out some things. That's where you get the most of the learning, right? And we'll also look at convolutions and image processing. So we'll definitely cover 1, 2, 3. If we have time for clustering and k-means, we'll go into it. If not, I'll still share the slides. You can take a look for assignment 1. So, or I'll just briefly talk about it. Okay. All right. So I want to start with a notebook on SVD. So let me just pause sharing here. Recording. Okay. So I just thought we can just walk through a simple example. This is a notebook. So, you'll be using something like this for your assignment 1, and maybe something that's already been covered by our TA in our quiz section. But I just wanted to highlight a couple of things that might be helpful for us to understand things better. So obviously we're using NumPy library. So import NumPy as NP. And then there's something called linear algebra library, linalg. So I'm calling it as LA. So let's import it. Okay. So define a 3x3 matrix. So just for the purpose of this, I'm just like making it very simple. So here's a 3x3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 10. Notice the 9 is missing. There's a reason for that. So let's compute the SVD. So we spoke about SVD last time. So the linear algebra library is going to give you access to the SVD. So this is giving us a full SVD because we haven't specified any K, for instance. There are also variations on this library where you can actually say, I just want to compute SVD to this factor K. And that could be more efficient in practice than computing a full SVD and then truncating it, right? Like if you have like a 10,000 by 10,000 matrix, you need to compute a full SVD. Any guesses on what the computational complexity is for computing an SVD?
Just the size of the matrix?
It's more than the size of the matrix. It's n cube. So, or if it's an n by n matrix, it's n cube. So it's a cubic in one of the dimensions. So it's actually pretty expensive to compute a full SVD. So you'll see that with 3x3 matrix, it's very easy. You go to 1000 by 1000 matrix, it'll take a little bit more time. And you can test this by generating random matrices. So instead of defining a specific matrix, you can have a random matrix here of some size. And then compute the SVD and see how much time it takes, right? Just time it. And then you go to 10,000 by 10,000, it'll take many, many seconds or even a minute. And then after a while, it'll just crash because there's not enough memory. So, so SVD is actually expensive. So there are efficient libraries to compute reduced SVD, which is of order n squared k. So for instance, if your k is like 100, but your n keeps increasing, then it's actually the size of the matrix like John mentioned, because k is a constant, right? So there is an algorithm for randomized SVD, which can compute it efficiently. So it might be part of the linear algebra package, or maybe it's part of scikit-learn. So that is something that you would actually use in a real implementation. You would not actually compute the full SVD and then truncate it. Okay, but let's say just those are some fine details. But let's say we want to use a full SVD for now. So you can see there are 3 matrices that SVD outputs, right? U, S, and V. So we spoke about this. U and V are orthogonal, and then S is a diagonal matrix. But if you look at what S returns here, it's just a vector. It's not a matrix. And that makes sense because it's returning the matrix of it's returning the vector of the diagonal entries of that matrix. So it's efficient, right? Why would you return a matrix with zeros? It's just taking up extra space. So let's look at it. So I'm going to execute. So this is U. you can see this is an orthogonal matrix, right? And then let's round it to 1 decimal place. So this is what it looks like, round it to 1 decimal place. Let's round V to 1 decimal place and S to 1 decimal place. So you can see S is actually a vector of size 3. That makes sense. There are 3 singular values. You can only have as many singular values as the minimum dimension of the matrix. So let's say you have a rectangular matrix, then the number of singular values will be the minimum of the 2 dimensions. If it's square, obviously it will be n. But it could be fewer. Like you'll have singular values, as many singular values as the dimension of the matrix. What happened? Sorry. Yeah, so you'll have as many singular values as one of the dimensions of the matrix. However, some of the singular values can be 0. So you can see here that, what is this? Yeah, so here S has all non-zero singular values. So, I'll just do something here. I said I skipped 9 and went to 10, and there is a reason for it. So let's say I change it to 9. Okay, so let's recompute the SVD. Okay. Okay, look at this. Look at the last singular value. That's basically 0 because it's not full rank. Yeah. Let me go back, change it. All right. Okay, so this is V. So we have U, S, and V. All right. So let's take the inner product of the first column of V with the second column of V, right? Oh, that's 0. That makes sense. We said V is orthonormal, U is orthonormal. So when you take cross, dot products of columns that are different, you get zeros. And like you can have V be 1000 by 1000, and you can take any 2 columns and they are different, you'll have 0. That's what orthogonal means. They are all perpendicular to each other, right? The vectors are all perpendicular. Okay, so this makes sense. How about if we just take the dot product of the column with itself? So I'm just picking the first column, but you can pick any column. You get 1. This also makes sense. This is the normal property that we spoke about last time. It's orthogonal and normal. So that's normalized. So U's and V's are normalized. So if U's and V's are normalized, what is giving us the scaling? It is S. Because your matrix can have a different scaling, right? You can multiply a matrix, you can divide a matrix, you can have higher magnitude, lower magnitude. But what is deciding the scale? The scale is decided by S. So S can have very high magnitude singular values or very low, but U and V are always normalized. Okay, this should also be straightforward. Okay, let's do reduced SVD after having computed the full SVD. So this is a less efficient way of doing it, but just for the sake of illustration. So what would I do? Let's say K equals 2. I want to pick K equals 2. So K can be between 1 and 3, right? So I say I want to do K equals 2. So I only want to preserve the first 2 factors. Then what I would do is I'd create new U, V, and S. So U tilde would be the first 2 columns of U. This is how you represent it, right? And V tilde, in this case, you have to be careful about how is the multiplication happening. So the multiplication here is not USV transpose, it's actually USV. So the product of U, S, and V gives you A. So which means I need to look at the rows of V and the columns of U. If it was USV transpose, I would be looking at the columns of U and the columns of V. So this is a matter of convention. So here, NumPy is returning me it in this format. So I need to look at the rows of V. So that's why I'm indexing the first 2 rows of V, whereas I'm indexing the first 2 columns of U, right? So that's the difference between how I'm building the U and V reduced SVD. And then S tilde is the first 2 elements of S. Because S is now a vector, I only preserve the first 2 elements, the top 2 elements. Yeah, this makes sense. So this is what U looks like. You can see it has 3 rows and 2 columns. Yeah, that makes sense. I'm picking the first 2 columns of U. S tilde, it has 2 entries, 2 non-zero entries. That makes sense, the top 2 singular values. So you can see these are the top 2, right? 17.4 and 0.87. What did we have earlier? 17.4, 0.9, and 0.2. This is rounded, so we ignored the 0.2. We kind of threw away. So we said we keep some and we throw away some. So we threw away 0.2 and we kept the first two here. Okay, so that's S tilde. And then V tilde, okay, so V tilde is actually 2 by 3 because, that's how it is. So I'll probably demonstrate it pictorially so you have a better idea of how this is happening. But I just want to run through the code. So let's check if A equals USV. If USV is the SVD of A, then if you multiply U, matrix multiply U and S, and matrix multiply S and V, and put it all together, you should get A. How do you check that? Well, we just take the norm, the difference between the matrix. So here's actually A, right? I'm saying X, but it's A. We call it A. But anyway, X is nice because it's a data matrix. So we're looking at the difference between the matrix you started out with and USV, and you can take some norm of it. So here, this F refers to Frobenius norm. So here maybe we're taking some other norm, but let's say, do we do it this way? Does it work? Yeah, it doesn't work. So, okay, maybe fro. No? Okay, maybe small fro. Yeah, okay, great. So small fro worked. So Frobenius norm is basically the Euclidean norm. So it's less like the L2 distance, right? How many of us are familiar with the L2 distance? You've seen it before between two vectors? Yes, no? No? So L2 distance is basically you take each entry of one vector and the other vector, subtract it, square it, sum it up, and take the square root. Okay, so it's telling you what's the average difference between, or the total difference between the two vectors. Okay, so this is, here, we're actually looking at the total difference between X and USV, and it is essentially 0. So this makes sense. It has to make sense. I mean, if it was not 0, then your calculation is wrong. Maybe you are multiplying USV transpose because you got the SVD. It has to perfectly factor. X has to be U times S times V. So that is what this is saying, that you're getting 0. So this makes sense. This is a valid SVD. Okay. So this specific U, this specific S, this specific V that we just computed, when multiplied, is equal to the A that we started out with, right? Okay. So yeah, I think we'll talk about two things when we get out of this. One is the shapes, and also we'll talk about Euclidean distance. Okay, let's look at the percentage difference between X and the reduced SVD. So if I didn't reduce it, USV are not reduced, right? We didn't do anything with USV. So we got that it's a perfect factor. So you get 0 as the distance. But what if you reduce it? So how do you reduce it? Well, we already reduced it using U tilde, S tilde, and V tilde, which we computed earlier, right? By picking out the first two columns, first two. So we talked about it last time. So if I use reduced SVD, let's look at what the difference is. And I'm looking at a relative difference. So you see, I'm taking a norm, the difference between, absolute difference between this matrix A and the reduced SVD factors multiplied together. However, that magnitude can be high or low. We don't know how to scale it. So to scale it, I'm dividing it by the norm of A. So I get a relative, I get to know relative to the norm of A or the magnitude of A, what is the change? So relatively speaking, it should not be too high. But absolutely speaking, you can have high magnitudes and you may not be able to make sense of it. So we always take relative percentage difference for that reason. So here it's a percentage, so I'd multiply by 100 as well, right? So percentage tells me more concretely what the error is. So the error is 1%. So by preserving the top two factors, I'm only incurring a percentage error of 1%. Yeah, so this makes sense. So that means the top two factors are capturing most of the information of the matrix A, even in this small example, right? Yeah. Okay, so a few more things, and I'll share this notebook after the class so you can play around with it as well. Some shapes. So shape of U tilde 3 by 2, shape of V tilde 2 by 3, shape of the, so this, you see this operation, it's interesting. It's np.diag of S tilde. So S tilde is a vector. np.diag takes a vector and makes it into a diagonal matrix, where everything else is 0 except the diagonals, right? And the diagonals are given by SLD. So that's shape is 2 by 2. That makes sense. And the shape of, what is this? Utility times A stack. Yeah. So this is the, when you multiply U and S, you get a shape 3 by 2. And then I'm going to multiply it by V till D, which is 2 by 3. So the shapes align. The inner dimensions align. So this is just checking on that. And what's going on here? Oh, this is something else. Okay. I don't think this is something useful. Yeah, and this is like a rounded version of U till D, V till D, and S till D to 1 decimal place. Okay. So you just want to look at what these U's, S, and V's produce. You get something like this. All right. So hopefully that gives us more of a context and understanding into how you would numerically go through SVD. Any questions on this notebook before we move on? Yeah, feel free to ask a question because any question you have might be something someone else has as well. Okay. All right, let's move on. So if you didn't ask questions, I'm assuming you got it 100%. Okay. All right, so let's move back to our just going to pause it. Okay, so so that was a notebook on SVD that we just went through. So now using that notebook, let's kind of look at this in-class exercise. Again, when you actually work things out, that's when your understanding becomes solid. So let's take the same example we had in the notebook. So we have this matrix X, 1, 2, 3, 4, 5, 6, 7, 8, 10. And then we did the reduced SVD computation. So we've just went through this. So this is U till D, V till D, and S till D, the matrix, diagonal matrix for K equals 2, right? And it's been, so here's another thing I want you to note. It's rounded to 1 decimal place. So it's not exactly what we obtained through the NumPy. We rounded it as well. Okay, keeping that in mind, the question we have here, which you can maybe answer on the poll, and if you don't have access on the poll, just kind of work it out for yourself and, you know, do it anyway, is which of the following is true? So just take a look at this and, you know, take a minute to answer it. Okay, did you guys have get the time to think about this? Feel free to shout out your answer. Or you can also put in the chat, whatever works for you. Okay, anyone? Yeah.
I think it's like close to 0 and close to 0 for both.
Yes. Yep. It's close to 0, but doesn't have to be 0. It could be 0, but you've already seen the U's and V's from the notebook, right? What happens is when you round it off, you're going to lose some of those decimal places that are going to make it almost orthogonal, but not exactly. But if, right? So, but if you didn't round it off, you just preserved it and you still, you know, did the reduce SVD, you would have exactly 0. So even if you did reduce SVD, your columns of U or rows of V still remain orthogonal because it's just from the same set. You've kind of reduced it, but you've not changed any of them. But since we rounded it, it's kind of reduced. Sorry, it's close to 0. Okay. Oh, we have one more. All right. Yeah, okay, let's take a look at, is it theoretically exactly equals to 0? Yes. If you did not round it, it is theoretically and practically exactly 0. I mean, you will, if you did it in NumPy, you will get 10 to the negative 16 because there is, floating point arithmetic issues. But you can consider 10 to the negative 16 as 0 if you didn't round off any of the values. So that's the very interesting property of SVD, right? So these U's and V's have that. Okay, let's look at one more exercise again to deepen our understanding. So we replaced 10 by 9 here. That's what's changed. Yeah, so it is, it's 1, right? So the number of so here's an interesting fact about matrix rank. Matrix rank is just the number of singular values, non-zero singular values in a matrix. So they have to be equal to each other. Like you cannot have a different matrix rank, and because that's a definition. I mean, there are multiple definitions for a matrix rank, but this is also a definition, right? If you refresh your linear algebra concepts, you'll see matrix rank is also the number of linearly independent columns in a matrix, right? So what happens? Why is the rank 2? Well, if you look at this, you can probably construct one of the rows from the other 2 rows. So that's probably why, like you can find some way to combine the first 2 rows or the first 2 columns to get the other column. So there's some linear relationship. So that means only 2 columns mattered to describe the whole matrix. The third column was dependent on those. But that's one definition of matrix rank. But if you did the SVD, then matrix rank is also the number of non-zero singular values. So that's why. We also saw, actually, when we went through the notebook, we saw that the singular value went to 0. If you remember, the third singular value went to 0. Okay, cool. All right, so I think I wanted to mention a few more things here to, this we may not go through this much again, but it's good to spend some time on it in the beginning so that your fundamentals on matrices is refreshed. And there's a lot of cool things about matrices and how you operate on them that so let's look at a couple of things. So one I want to mention was going back when we did this U tilde, S tilde, V tilde. So when we said it's 3 by 2, just imagine in your mind it looks like this. It's taller than wide, right? And then S tilde is 2 by 2, so it's square, and then V tilde is 2 by 3. So whatever we saw in that notebook earlier, if you wanted to visualize it in your mind, I would do it this way, right? And the inner dimensions match up, right? These two match up, these two match up. So this cannot be 3 by 2 because then the inner dimensions don't match up. So that's how you know you got it right or wrong. Okay, so just in terms of visualization, so always like looking at matrices, kind of visualize it. Is it tall? Is it wide? What is going on? How am I multiplying it? Usually you multiply a tall matrix with a wide matrix. You don't multiply a tall with a tall matrix because the dimensions will not match up, right? Or you would multiply a wide matrix with a tall matrix, or you would multiply a square matrix with a square matrix. So that's the intuition, right? Okay, so this is one thing I want to mention. The second thing is just how you multiply matrices. And you may not have seen this before. Maybe you have seen matrix multiplication, but there is at least two ways to multiply matrices. So let's say you had 1, 2, 3, 4, and then 7, 8, 9, 10. So if I want to get the, right, I want to multiply. If I want to get, let's say, the first element, So what is this? It's 1 times 7 plus 2 times 9. So I go this way and this way, right? And I would do the same thing for something else. So let's say I want to get this element. It's this times this. So it's 3 times 8 plus 4 times 10. Yeah. So this is something that you might have seen before. So what is this? It's actually dot product between different vectors. It's dot product between a row vector and a column vector, right? Every single entry of a matrix is a dot product between the row vector of the first matrix and a column vector of the second matrix. And how do you index it? Well, for instance, here it's 2, 2, right? So it's a second row, second column. So this is, let's say, U2, and this is V2. So this is equal to U2 dot V2, right? And then the same thing holds for this one. You'd say this is U1 dot V1. So this is U1 and this is V1. And conversely, if you look at something else like here, you'd say this is, what is this? Using the same kind of convention. Anyone?
U2 times V1.
It's U2 dot V1, right? Because it's the second row and the first column. So it's very intuitive. You're looking at the second row here and you're looking at the first column here. So you should take the second row from the U matrix and then take the first column from the V matrix and then multiply it and you get this. Yeah. So this is an intuitive way of understanding matrix multiplication. Is just dot products corresponding to those rows and columns of the respective matrices. So this is one way of multiplying these two matrices. Let's look at the second way. I mean, eventually it's the same thing, but when you think of, for instance, the SVD decomposition, it helps to understand the second way as well. So let's say you have 1, 2, 3, 4, and then 7, 9, 8, 10. I want to multiply it. So this is, you can say this is equal to 7 times 1, 3 plus 9 times 2, 4. So that's the first column. And then you have 8 times 1, 3 plus 10 times 2, 4. It's the same thing, but because eventually you're just doing, if you look at this, you're doing a dot product between this and this. So all of that holds true, but it does make a difference because when you think in terms of decompositions, you can decompose matrix multiplication in this nice way where you're taking each column and multiplying it by the elements here and then summing it up. So this way of doing multiplication is what is useful to understand how the SVD decomposition happens, right? And we'll see that shortly. Yeah, so basically, if you had something like, let's say you had U1, U2, U3. So in the previous method, you're looking at the rows of U, right? Now we're looking at the columns of U to multiply things out. So let's say you had U1 through UN, and then we had something else. Let's say we had V1, V2 through VM. So let's say this inner dimensions match up. So it's a valid multiplication. So what you would do now is you would say this is equal to, let's call this the U matrix. It's the U matrix times V1, U matrix times V2, U matrix times V3, and so on, U matrix times Vn. So the result here, let's call this X, is U times V. It's actually equal to this. Why is that? Because U V1 is U1 V11 plus U2 V22 plus U3 V33 plus so on. So notice this is a vector, but this is a scalar. So you're just scaling every column in U, right, by the appropriate weights. The weights are given by V1 and then summing it up. Why is this useful? Well, we saw the Eigen Faces last time. You remember we took every Eigen Face and multiplied it with a weight and then summed it up. Well, these are those weights that show up in those Eigen Faces, right? So this way of adding things is coming from this way of doing the multiplication. Okay, so understanding how you do this, is really helpful. Okay, any questions on this? The second way of doing the multiplication. I mean, however you do the multiplication, you get the same result, but the way you decompose it makes it easier to understand certain things or certain models. Okay. So that's something I want to mention here. Let's kind of make it more practical for us. So let's take a look at this. And I would ask you to apply the second way of multiplying matrices in this in-class exercise. Okay, let's take a minute to do this. Okay, so yeah, happy to see people working on the math here. So hopefully you got the first option as the answer, right? Because it's very intuitive. So you want a second column, so you take 3 times 1, 4, plus 4 times 2, 5. So this is the second way of multiplying things, right? And you can see, oh yeah, there's 11 there, and there's 32. Yeah, okay, makes sense. Okay, so this is probably where you will really understand the decomposition of SVD even better, where we'll be using the second way of multiplying two matrices. So let's look at SVD of X is U sigma V. Well, we said V transpose. It depends on how you want to set it up. Let's just say V. It doesn't really matter so much. But let's look at this. So I'll break it down into U1, U2. Say there are n columns, so UN. And then sigma is sigma 1, sigma 2, sigma n. So these are the singular values, right? There's n of them. And remaining is 0. It's a diagonal matrix. And then you have V. So let's just take this part here. So in the first way of, in the second way of multiplying matrices, let's say I want to get the first element, first column of this matrix multiplication. I take this and multiply it by U, right? But all the other elements here are 0. So it ends up being sigma 1 U1, because it's 0 times U2 plus 0 times U3, and all of that is 0. And the second one is sigma 2 times U2. The third one is sigma 3 times U3, and so on. Sigma n times Un times V. Okay. So now X is equal to sigma 1 U1, sigma 2 U2, so on, sigma n Un. And now we want to break up V in a way that we can do, this matrix multiplication. So here we'll actually do it the other way. So we'll say this is V1 transpose, V2 transpose, Vn transpose. So we break V into the rows of V instead of looking at the columns. The reason is there is one more, there is another math that's operating here, is you can take this and multiply with this, and then you can take this and multiply with this, and you get matrices from each of them. Okay, it's the same as when you take dot products of two vectors, except here you're taking outer products instead of inner products. So what does this give us? It gives sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus so on, sigma n Un Vn transpose. So this is really cool and very important to understand. This is the additive decomposition of the data matrix X into n rank 1 matrices. So why n rank 1? Well, look at this, U1 V1 transpose. Again, when you look at this, imagine the shape of it. Okay, because you're staring at symbols here, it's good to imagine what's happening. So U1 is this, right? Because it's a column. V1 transpose, this notation itself tells you, oh, there's some row element going on here. So you're multiplying two vectors in an outer product sense, and you get a matrix, right? because you just multiply each element here with all the elements here. You multiply this with all the elements. You multiply this with all the elements. So basically, you're getting a full matrix. So, but it only is a product of, you know, two vectors. So that's why this is a rank 1 matrix. Also, if you did SVD on this, you would get one singular value. The singular value of this would be 1. Because these are the factors. U and V1 transpose are the factors. They're orthogonal. They are, you know, they have a norm of 1. So these are the factors. But it's scaled by sigma 1, right? And then this is scaled by sigma 2. This is scaled by sigma 3. So when we cut off things, you know, we discussed this last time. So if you cut off things at sigma k, uk, vk transpose, and you say keep, and then throw away, you're basically throwing away all these other things that you can add on, and you only keep these. Yeah, first K. So I think a couple of you asked me after class last time, how do you get this additive decomposition? This is how you get it. Okay. Okay, why is this useful? Let's look at it. So, you know, everything that we do here we'll discuss in this course. We will take every mathematical concept, everything that we discuss, and tie it back to a real application. So nothing is going waste. But on the other hand, mathematical concepts that seem like, oh, where would I use it, actually do have applications. You just have to dig for it. So, but here, let's again tie this back to a real world application. So we have this additive decomposition. Let's say you pick a K. That means you throw away the rest, you keep the first K. How does this help me understand, let's say, image decomposition? Okay, let's go back to Eigen Faces. So we said that you have a bunch of faces, and each face is a column in X, right? So if you have an X matrix, so this might be this image. This would be this image. This would be this, and so on. So each column is an image that is represented as a vector. So so with images, you have to be comfortable going from a matrix to a vector and vector to a matrix. It's the same information. It's just that you encode it as a vector or you encode it as a matrix. Yeah, it's intuitive to think of an image as a matrix, right? But why do we encode it as a vector? Because, well, we want to deal with a matrix at the end of the day, and we have a bunch of images. So then we'll become a tensor. So you can make it a tensor as well, because we will be dealing with tensor math when we get to convolution neural networks. But for now, it's easier to just think of an image as a vector and then just put them together. Okay, so that's X, our data matrix, a matrix of images. And then we said these are the Eigen Faces. So what are these? Well, when we said X is equal to U SV transpose, this U here, if you were to decompose U1, U2, and then UK, let's say you only keep K, right? You don't keep all. So this U1 is this guy here. This U2 is this guy. Well, this is a matrix, but this is a vector. So this is where you have to connect. Oh, it's a vector here, but this vector can be converted into a matrix, and that's what we are displaying as an image. Yeah. If this is, let's say, a 100 by 100, or let's make it more. Say it's 100 by 200 pixel. What would be the dimension of U1? So we are saying U1 is the same as that eigenface 0, but U1 is now a vector. It's not a matrix. So how would you represent that image as a vector, and what would be its dimension? So we're just asking for the dimension here. So how would you get U1 from the eigenface? Well, basically you would take each column and then stack it, right? Comes here, this comes here, this comes here, and so on. And then this becomes U1. So now, is it easy? Yeah, okay. Okay, so note how you're saying it. Are you saying 1 by 20K or 20K by 1? That also matters. 20k by 1 means it's a column vector. 1 by 20k means it's a row vector. The way we have put it here, these are column vectors. So the dimension here would be 20k by 1. So the 1 represents one column. If you said 1 by 20k, there's 20k columns, or the same as one row. Okay, does it make sense now? Why we are going back and forth between matrix and vectors? So we did an SVD on a matrix of images where each image is stacked as a vector, and then you get a U, which is again a matrix of Eigen Faces represented as column vectors, which can then be visualized. So once you do the SVD, you'll get a column vector. You like visualize a column vector. You will need to convert the column vector, which is stacked, right? Pixels are stacked, move it back to a matrix, and then visualize it. Okay. Or if you have visual, convert it back to a column vector and then put it back there. Okay, does it make sense? All right, so this is something, hopefully by now it should be more clear on how we are doing this. And this is the most, beautiful thing I would say is if you have, let's say x phi. So this is image phi, right? So we're saying x1, x2, x, let's say 100 equals u1, u2, so on, u. Maybe you only have, how many of these? So you only have 12. You only keep k equals 12, right? So this, let's say k equals 12. So I only have 12 reduced SVD. So keep it to 12. And then you have something else here. Let's call it a weight matrix. That weight matrix is a combination of sigma and V transpose, right? So let's call this W. So then I have something like W1, W2, W 100, because there's 100 of these images. So now this is x phi. This is the fifth image in my data matrix represented as a column vector. Okay. So if I want to get x phi, what do I do? Well, this x phi is taking u phi and multiplying it. Sorry, it's taking, it's taking w phi, and it's multiplying the whole U matrix with w phi. Yeah. So x phi is equal to u1 w phi 1. So the first element of the fifth column vector, the fifth weight vector, u2 times w phi 2 plus u3 times w phi 3 plus so on, u12 times w phi 12. Okay, so this is u1 and this is w phi 1. This is u2, this is w phi 2. So when we say this image can be decomposed into these Eigen Faces and then weighted in this way, the math behind it is you take the U matrix, all these Eigen Faces are U's, and then you compute the weights. The weights are coming from sigma and V. Combine them together, you get a weight matrix. And then from there, you're able to decompose this. So once you get the SVD, you can do a lot of things. You can decompose, you can do this, you can, compress things. So we've looked at two use cases of SVD so far. One is compression and another is decomposition, understanding the components of an image. How can an image be represented better? Okay. I think we've covered this. Okay, cool. Any questions on this before we move on? All right. Yeah, the key thing to remember is Eigen Faces or these U's are giving you basis. They're giving you a basis to understand any image. But images that were specifically trained, or I would say images from which you actually learned the SVD, or in this case, the X. So whichever images you were using to decompose X or to compute the SVD, those images are giving you a basis or a basic set of faces that can be used to understand any of these images. So you can think of use as giving you a basis, right? So that's one of the key things here. Okay. And also these bases are orthogonal. So which means if you took this matrix and this matrix, these two faces and take a dot product, you get 0. You take any of these and take a dot product, you get 0. So these faces are somehow different. They're capturing different pieces of information. What is orthogonality here? Orthogonality represents different pieces of information. So you want enough different pieces of information, in this case, k equals 12, that you can basically understand any image. Yeah. So maybe I'll mention that here. Orthogonality. All right. Okay. One more thing. How many of us have heard of PCA before? Show of hands. PCA. Okay, one of it. So PCA stands for Principal Component Analysis. Okay, this is a very famous. So if you had a data science interview, you might get a question on PCA. Okay, you go to your interview, they'll be like, can you tell me if PCA is robust to outliers? You're like, what? So this is where you want to pay attention to that, right? So this is a very popular method in statistics. But what is PCA? PCA is, again, giving you an understanding of data. PCA is, basically the U vectors. The PCA dimensions refer to the U vector. So this is, let's say, U1, this is U2. So if you did a SVD on the data, so what is data here? All of these are data points, right? They're two-dimensional. Okay, so maybe I take x equals x1, x2, so on, xn, where each of them is a two-dimensional point. So this is 1x, this is 1x. So maybe this is x10, this is x100, whatever, right? This is x50. You take that, this is your X matrix, then you say, okay, U sigma V transpose. I did my SVD. All right. Now take this U, and this gives you the principal components. So what is principal component? Principal component is telling you the direction of maximum variance. So that's a new concept. So look at the variance of the data here. Which direction is there more variance in the principal component direction 1 or principal component direction 2? It's 1, right? So if you see, there is more spread in the data here. If you look at this axis, there is less spread, isn't it? It's obvious, right? It's intuitive. There's more data spread across. So the direction of maximum variance is captured by the first singular vector or first eigenvector. Interesting. Another interpretation of SVD in terms of statistical understanding of data. It's the same SVD, but you're giving it a new interpretation. You're understanding it in a different way. Also, you can say, well, if I take any data point, I just scale U1 by some value, I'm going to approximate that data point very well, right? So let's say I take this data point here. This is, let's say, X78. My U1 is pointing in this direction, right? U1 is pointing in this direction. So I'm going to approximate X78 by X tilde 78 here. So it's going to be very close. So the principal components also give you the direction in which most of the data lie. You can approximate well. It's also the direction of maximum variance. So pretty interesting to understand. And PCA is not robust to outliers. So this is a question you'll get in a data science interview. You have an outlier here, the direction will change. Even like a couple of outliers can skew off the direction. Okay. So that's a little bit on PCA. So that's why we spend a lot of time on SVD, because it has so many connections. All right, I think it's 5 p.m. Let's maybe take a quick 3-minute water break. We'll come back. Okay, let's continue. So assignment 1, how many of us have already tried SVD for data compression for assignment 1? Show of hands. Okay, 1, 2 people. Okay. Okay, let me just go through this. So there are many data compression techniques, but I would recommend you using SVD because you've already spent a lot of time on it and it's a new technique you've learned, so might as well apply it. So given an image I, so color image, right? I'm not using a color to describe a color image. Okay, so given a color image, let RGB be the corresponding channel matrices for the color image. So red, green, blue channels. So if you want to think about it, let's say have this is your X image, and then this is connected to your R matrix, G matrix, and then B matrix, right? So R, G, B. Okay, so every color image will have a R matrix, G matrix, and a B matrix, right? Which will tell you how much of the red, green, blue are present in any given pixel in the image. Okay. So what we'll do is we'll compute SVD of R, G, and B, which means you're computing 3 separate SVDs. Yeah. Pick a K for all the 3 matrices. Pick a K. I want to preserve 20 factors or whatever is your K, and compute the reduced SVD factors for RGB. But we as we looked at in the last lecture, the K is connected to the compression size. So if you want to get different levels of compression, you would pick different Ks. So don't pick 1K, pick different Ks that give you different levels of compression. And then you compute the reconstruct at R tilde, G tilde, B tilde, right? So what is R tilde? R tilde is U tilde R, sigma tilde R, V tilde R transpose, right? For the red channel matrix, compute the U sigma V, reduce it, U, reduce the sigma, reduce the V, combine it together. The product of that is what we call R tilde. And the same thing for G and same thing for B. Okay. Because why are we doing it? But because we want to visualize it again. You want to, like, it's not enough to compute the SVD. I want to actually visualize how it would be if I use the compressed version of the image and put it back together. How would it look like? And that's how you're telling if the reconstruction quality is good or bad for a particular compression. So I need to do this. So this, is very important. Reconstruction is also a part of, this SVD process, right? And then use the R tilde, G tilde, B tilde to reconstruct the image. Yeah, so we spoke about it. How would you do that? Well, just R tilde, G tilde, B tilde informs my matrix, take the different R's, G's, B's, and then fill out all the pixels and then visualize it. Okay, so you'll have libraries to do that. And then plot the reconstructed images for at least 3 different compression factors. So keep in mind, we said, if you want a compression factor of 5, what is the maximum K you can have? We did that computation in the last lecture, right? So that is what you will use here. Let's say you want a compression factor of 2, compression factor of 5, compression factor of 10. I need to pick an appropriate K for each of these compression factors, right? Or you can do trial and error, but it's easier to just be a little bit smart about it and then pick a K appropriately, and you'll be roughly in the ballpark of the compression. So when you actually save the files, save the matrices, you'll see that the compression factors is roughly that. And then when you visualize it, you will see, oh, for a compression factor of 2, these images compare and they seem very close to each other. But for 5, there is a loss. For 10, there's a lot of loss. Right? Yeah. Does it sound good? So a few steps here, but it's not too complicated. Okay. So the next topic we'll be moving on is to look at image processing with convolutions. Again, this might be a refresher for some of us and maybe not. So what is a convolution? Convolution is a mathematical operation of sliding a convolution matrix kernel as a window through your input matrix. And what do we do when we slide? We're essentially taking a dot product. So you're not doing matrix multiplication. So let's say I have a sliding window here. Okay. So what am I doing here? I'm taking my original matrix from here. I'm like, this is my submatrix. And this is my convolution. And then I'm taking a dot product. It's not a matrix product. So basically multiplying every element. So you see the dot product is more efficient than a matrix product for two matrices. Do you see that? If you multiply two matrices, the complexity is order n cubed, right? If you dot two matrices, what is the complexity?
Will be n square.
N squared. Why? Because you're taking every element in this matrix, multiplying with the element in this matrix, and then that's it. And maybe summing it up. Summing it up is also n squared. So this is important to know, working with complexity. Again, if you have an interview, you'll have a question on complexity. What's the computational complexity of this operation? So it's good to start thinking along these lines. Yeah. So the computational complexity of this dot product is n squared, right? Where n is the size of the window. So let's say I have 3 by 3 window, it's order 3 square. But I'm not doing it once. I'm actually sliding it all the way through the first set of rows, and then in the next set of rows, and then the next set of rows. And that's how I go from here to here. So here I've applied a box blur kernel. So I think it looks like this. Yeah, maybe 4, -1, -1, -1. Oh, wait, it's box blur. Sorry. So it's probably 1, 1, 1, 1, 1, 1, 1, 1, 1, divided by 9. So we looked at it last time. So this is my C here. It's a 3 by 3 window. So I take this 3 by 3 window, and this is what I'm sliding here, right? So I slide, 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 slide. And every time I slide, I get a scalar. I don't get a matrix. Why? Because I multiply dot the two matrices. A dot product is always a scalar. And I take that scalar and I put it here. Right? And that's how I fill the matrix. And here, obviously, because of the size of the convolution, you will not be able to go all the way. You will have to stop at the end. So that's where you can either pad to get the same dimension, or you will have a reduced dimension result. For instance, here you'll be reducing it by you'll be reducing it by 2 because you have a 3 by 3 matrix. If you have a 5 by 5 matrix, you'll be reducing by 4, right? Because you cannot go all the way. And then you do the same thing. You slide it down, and again you keep doing this, and then keep taking dot products. And so that's how this will start filling up here. Sorry, I'm spoiling the image here. But so this is how you would just get into that convolution operation, right? And we spoke about this. This is an averaging. It's averaging. Basically, you say take a window and then sum it all up and then divide by 9. That's an averaging operation. So you're averaging the pixel values, and that is why it is blurred, right? Like if things are white and gray, you kind of like mix it up, it's gray. Everything's gray. So it's going to kind of average things out. So that makes sense. So box blur. So here's, I guess, this is also an illustration of that. So you have a kernel, box blur kernel, 1/9. You dot it with this, and this one operation gives you this scalar, 22 point whatever, and you fill it in here, and then you slide it again, and then you get something else, maybe 32. You slide it, keep going that way. Okay, so pretty straightforward. All right, so let's test our understanding on box blur through this in-class exercise. It shouldn't take more than like a minute, so feel free to just take a crack at this. So we're using a 2x2 box blur. What does that look like? So you still have one once, but you divide it by something else. What do you divide by? 4, yeah. Because you're averaging, it's the number of elements in the window. The number of elements in the window is 4. So you divide by 4. So as you change the dimension, so you divide basically by n squared, where n is the number of rows or columns in that window. Okay. So let's convolve and look at what the convolution result looks like. All right. So that makes sense. Okay. So that's a box blur kernel. So that's how you will go from here to here. You get a blurry image when you apply that convolution kernel to this image. Okay. Okay, let's look at a different kernel. So edge detection kernel. This is a very simple edge detection kernel. It's I think it's called the Laplace. Is it Laplacian? Yeah, it's a Laplacian kernel. So we'll look into what this is. But what do I want to do? I want to detect edges. So I want to detect where things are changing, right? So for instance, here, there's a change. There's a change here, right? So edges are where, oh, there's something there's a transition. So those transitions should be highlighted, right? So there's highlight here, highlighting it here. There's a nose, you want to highlight that. So all of that, this is like this. So this is the edge detection kernel. So you apply you convolve with this, the Laplacian kernel with this original image, and you get the edge detection image as a result. So what does the kernel look like? There's a couple of ways of understanding it. So we already looked at the blurring kernel. So this is box blur. So if you remove the averaged version of the image from the original image, then you get something that looks like an edge. This is one of the ways to get the edge detection, right? So this is edge. So that's one way of understanding it. But if you look into the specifics of it, yeah, there's a couple of ways of looking at it. Let's think about it. So what is this equal to? This is equal to -1/9, -1/9, -1/9. And then 8/9. Yeah. So if you look at what is the sum of all the elements in this matrix? So this is my C. So this is the C that was used to basically get this output, right? So X convol with C gives me the output. So what is the sum of the elements in C? 0, right? Because there's 8 elements on the edge and there's 1 sitting right there. And so it sums up to -8/9. So what does that mean? It means if the image isn't changing from pixel to pixel, the difference of the surrounding pixels and this pixel, the middle pixel, the pixel of interest, is going to be 0. So you're not doing much there. But when there is a change, when there is a transition, I'm going to have something that's non-zero. So that's how you're able to detect the edges. If there is no change, so this is an area of no change, for example. So here it's all going to be the same. But then as soon as I enter this area, so here I'm having a change. So this kernel is able to detect edges and changes because of this reason. It doesn't do anything when nothing's going on. But if something's going on, it's able to detect it. It's able to catch it when there's a transition. And the transition is not just left to right or up and down. It's like all around. Like there could be nonlinear transition. I mean, transitions could be in any direction, and it's able to detect it. Okay, so there's this is definitely one kernel. There's another kernel that was used to get this. So that's the Laplacian edge kernel. So very closely related to this. It looks like this. So again, if you notice, the sum of the elements in this matrix is 0, right? The difference between this one and this one is we also have zeros here instead of some non-zero element. So you are only looking up, left, right, and down. You're not looking diagonally. So this was looking diagonally. This is just looking up, left. So this is the Laplacian edge detection. So the Laplacian gives you something like this. This one gives you something like this. Okay. So this is one of the ways to do edge detection. There's other ways. There's other kernels that can detect edges too. For example, Sobel edge detection. Okay. I'll not spend time on this. There is a reference to a Wikipedia article on different kernels, and you can take a look. And that gives you a different kind of an edge. Yeah. It might be looking more smoother than this one. Right? This looks very grainy. So that's the reason to consider different edge detection kernels. Although they intuitively make sense, some of them have more smoother output for edge detection than the others. So the Sobel one is pretty popular. So you can use that in your assignment for edge detection, for instance. Okay. Okay, really quick in-class exercise. So let's say your convolution kernel looks like this. The question is, what happens when C is convolved with an image? Stick like this shouldn't take too long. Okay. So yeah, this kernel has a name. It's called the identity kernel because it leaves the image unchanged. Why is that? Because except the middle value in this matrix, everything else is 0. That means it ignores any other pixels around. So it doesn't take any information from the surrounding pixel. So it's not doing anything. It's just like copying this pixel into the new image, right? When you do the convolution. So that's why it leaves the image unchanged. Essentially, I mean, for the most part, because there's still that edge effect where you lose some columns, a couple of columns, but subject to that, it's all the same. Sharpening an image. So we looked at blurring an image. We looked at edge detection. So let's look at a kernel that can sharpen an image. So you can see this is a sharper version of this image. You may or may not prefer it, but you can see the details are more obvious, right? It's a little bit grainier. For example, you can see the face is a little bit grainier, but then the other things like the hat itself looks more detailed. The background looks more detailed as compared to the original image. So it makes it more sharper. There's more contrast. So how would you get a kernel that can sharpen things? So again, another intuitive way of understanding this is you take the original image and add the edges. So what's happening with the original image is, yes, it has all the information, but it's not capturing the places where things change. So very simple, just apply the edge detector, get an edge version of the image and add it to your original image and you get a sharpened image. So you can change your edge detector and you can get different sharpening kernels. So the kernels also add up, right? So let's say you have 0, 0, 0, 0, 1, 0, 0, 0, 0. So this is your identity kernel. We just looked at it. Plus, let's say I have a box blur kernel. So that looks like 4, -1, -1, -1, -1, 0, 0, 0, 0, because I am blurring it and then I'm adding it back to the image. So this is adding it back to the image and this is blurring it. So let's look at what the product, the sum is. The sum is 0, -1, 0, 0. Oh, sorry, -1, -1, -1. And then 4 plus 1 is 5. So it looks very close to the box blur kernel, but the middle value is higher. So the sum of all the entries in the sharpening kernel is not 0, because that means you're not doing anything. You want to do something. You want to sharpen where it makes sense. But you're sharpening basically at the edges. So that's what we notice here, right? The edges are getting sharpened. They're getting more delineated. So this is how you build intuition around kernels and what they do, right? You just have to play around with the matrices or, decompose. Again, this is another example of decomposition. It's an additive decomposition of the sharpening kernel in terms of the identity kernel and the box blur kernel. Okay, so this is a sharpening kernel that's based on box blur. So you can change the box blur. You can say, I want to do Gaussian blur. I want to do something else. But the formula to get a sharpening kernel from all of that is kind of similar, right? You can just add it to the NT. So yeah, there's a playground for the convolution kernel. I think maybe we'll just take a look at that as well. Meeting. Okay. So this is a playground that's available. You can take a look. So I uploaded this image on the left, and then you can see what kernels are being used here. So this is a box blur kernel. You can see all the values are 1, and you get the blurred image on the right. Yeah. So let's change it to an identity. So obviously it's 0s and 1 in the middle, and then you get the same exact image, right? There's no change. Let's change it to sharpen. So it sharpens. Again, the sharpening is probably done based on box blur. So maybe there are better ways to sharpen it. And then let's look at Gaussian blur. So there's a different blurring. So Gaussian blur is like the central pixels have more weightage, and then as you go away, it reduces. So instead of like it's a gradual reduction. So I think 5 by 5, you can see how it, yeah, here you can see. So this is a Gaussian blur of 5 by 5 size. So you can see the central pixel has the highest weightage, which makes sense. But as you go away, it kind of reduces in weightage. So instead of uniform, you're doing a Gaussian. So kind of, waning it slowly. So you give more weightage to pixels closer to the current pixel. And that's how this looks like. And there's other things. You can do your custom thing. Okay. So I've linked this in the references. So feel free to take a look and play around with it. Okay, great. So we took a look at that. Okay, we have like a few minutes left. All right, so we'll be moving to the next topic. So we've covered enough of convolutions that you can do the assignment 1. But feel free to, so any of these convolution kernels, right? Like I would focus on the intuition. Why is this sharpening? Why is this blurring? Why is this doing this? So asking that question will give you more than just trying, copy pasting it or whatever. So just kind of spend some time understanding why is it giving me this result. So building that intuition gives you much more, right, with convolutions. Okay. Okay, so next topic is on clustering of data or images. So we have a question on k-means in assignment 1. By the way, if you haven't started on assignment 1, do start. There's a lot of material in there that you need to, you'll have to work on. And as you see, but it's if you start early, you will be able to like do it without issues. Also, if it seems a little bit heavy to anyone, it's like you're catching up on a lot of background that we need for the course. So you might as well spend that time. And making sure your fundamentals are strong. Okay, so big picture, in terms of, we'll keep coming back to this big picture. So machine learning, we have 3 pillars: unsupervised learning, supervised learning, reinforcement learning. So we kind of check this off. This is our SVD. We spend a lot of time here. We're moving to this one, clustering. Right, so this is again falls under unsupervised learning because you do not have labels. So once we finish this, we'll go to supervised learning, right? And then we'll spend time, and that's where neural networks, deep learning, and all of that are going to show up. CNNs, so all of that will come in supervised learning. Reinforcement learning, we are not going to touch in this course because it's not so relevant for computer vision. Okay, so what is a clustering problem? If you recall, we said, let's say you have you go to a park and you see a bunch of flowers. So you see there is like the purple cluster, there is like the yellow cluster here, and there's other clusters. Well, let's say you went to Tulip Festival, you see a bunch of flowers in rows in Seattle. So those are all clusters, right? They're all arranged in groups. So the defining characteristic of clusters is, let's say in the context of flowers that are of the same type are close to each other. Flowers that are not of the same type are further away from each other, right? Yeah. So that's why we call them clusters. So you will not find a yellow flower here. Sometimes you do find it. If you went to a tulip festival, you'll have one yellow flower sticking in between a bunch of red tulips. That's an exception. So, but typically all the flowers are, clustered together. So the question is, given an image like this, or given data of this kind, can you circle the clusters and say this is a different cluster and this is one cluster and this is something else? So that is a clustering problem. You're not given labels. You're not told there are yellow flowers here, there are purple flowers. You're not told anything. You're just asked to do clustering. How do you do that? Again, you have this K that shows up in clustering as well. What is K? We had K in SVD, which is the number of factors. What is K here? Number of clusters,
Number
yeah.
of groups.
Yep. Very intuitive, right? So just like we had to pick a K for reduce SVD and it's connected to compression, you have to pick a K here as well, because that's going to tell you how many clusters you're going to group into. So it might turn out that you put these two in one cluster because they're close to each other, and the reason is you only had a K of 4. So maybe you pick the purple one, maybe you pick the red one, maybe you pick the white one, and then you pick this. So sometimes when you cluster, you will see, oh, why are these coming in together? Well, if that's the case, you need to increase K. So picking K is also an important problem in clustering. Typically, it's done, there are ways to pick K. Like sometimes this is my K I want to pick. And a lot of times you don't know what is the K to pick. So, but there are things like, there are metrics for inter-cluster distance and intra-cluster distance. So people try to see for what K is the intra-cluster distance small while the inter-cluster distance is large. So some of these metrics can be used to, identify a K. But yeah, so you have to pick a K for the clustering problem. Okay, and then difference between clustering and classification. So we haven't covered classification yet, but we did mention that classification falls under supervised learning, where you have a label Y along with X, where X is your input and Y is your target or output. For example, X is a flower and Y it's a yellow flower or it's a green flower. Oh, sorry, we don't have green flowers. It's a red flower, right? Whereas in clustering, you would just be given X. Here are some flowers. But or they may not even tell you it's flowers. Here are some images. Here are some objects. Figure out what you want to do with it. Bunch it up however you want, right? Okay. Some examples of clustering, digits clustering. You'll see this. It's a very popular data set called MNIST. People have published so many papers on this MNIST digits data set. A very popular one. It's a nice one because you see each row is a cluster, right? So yeah, I mean, each row represents a digit. There's 0, there's 1, there's 2. But each of these digits, even within a row, they look different. They're not the same. They're written differently. But to us, it's obvious. Like you look at this, let's say a kid looks at it, it says, oh, look, there's a line. The kid is doing clustering in its head. It doesn't know what the digit is, but it's saying, look, this one is different. So the kid has already done a clustering in their brain, and they said, I don't know what this is, but they look same, right? So that's an example of clustering. So taking an image of digits or taking an image of bunch of digits and being able to say there are, let's say you did k equals 10. So here for digits, it's easy, right? How do you pick k for digits? Well, yeah, there are 10 digits, of course. If I know there are digits in the images and that's what I want to identify, then obviously I'll pick k equals 10. And hopefully I'm able to separate the zeros from the ones, from the twos, from the threes, from the fours. Yeah. So here k equals 10 makes sense. Okay. So how do you do clustering? Actually, we're running a little bit out of time and I have to head out somewhere. So I would say for your assignment 1, use k-means or k-means plus plus. Either of these, you have libraries for it. And you have to pick a k though. So, and then see if that k makes sense for your problem, right? But we will go more into details of this in the next lecture as well, and how k-means works. What is k? What does it look like? But we are actually like only 4 minutes left, so we'll stop here, and I'll take maybe 1 or 2 questions, and then we're done for the day.